So we've agreed that by 2100, sea level is going to be somewhere between 3 and 6 feet higher, and possibly much higher than that, depending upon what happens to Greenland and to the Antarctic. Sea level rise comes from two sources. One is the expansion of the upper ocean because of the warming, and every fluid expands when it gets heated. The other thing is the addition of new water to the ocean that comes from the melting of land-based ice. Floating ice doesn't count, just like the ice cube in your glass of iced tea. And up until now, expansion probably has accounted for something more than half of all of the observed sea level rise. As we go farther into this century, all the predictions are that addition of new water will become more important. If you look along this California coast, the best estimates are that over the last 100 years, sea level has risen by about 8 inches. But if you look only at the last 2 decades, sea level rise along the California coast has almost not risen at all, and you heard a little bit about that in our first class, and it's largely because of what's called the PDO, the Pacific Decadal Oscillation, and it's an interaction of the wind field with El Nino, La Nina, and the recent paper within the last month by 2 people from Scripps, not the 2 that were here, is, though, that will all change and that we will probably see a more rapid rise of sea level along the California coast than in much of the rest of the world ocean. So we're going to catch up. And in terms of the areas that will be the most impacted, San Francisco Bay will suffer the most, but on the open ocean coast, the 2 counties that will have the greatest losses are Marin County and Orange County. And our first speaker is from Orange County, and I know at least a couple of you live in Orange County, and so you may have waterfront homes. Sea level rising is not something new. It's been going on throughout much of geologic time, and it didn't cause any particular issue because it's only been in the last short period of time that humans have built cities and all of the infrastructure close to the ocean. And for the last 2,000 to 3,000 years, sea level really has been pretty stable. It's only within the last few decades that it has started to take off. And the problem is that as sea level moves vertically, it advances laterally. So when sea level falls, the ocean withdraws from the land. When sea level rises, it invades the land, and it's been doing that for a long time. And sea level has been rising for about the last 18,000 years. And we need to mitigate, and the only real way to mitigate the rise in sea level is to reduce the levels of CO2 emissions to the atmosphere. But the problem is that even if we eliminate all CO2 emissions tomorrow, which we can't, sea level would continue to rise for decades to as much as a couple of centuries. We can make room for you, Dom, always. All right. So in addition to mitigation, we have no choice but to adapt. We have got to adapt. And we talked about different strategies. You can retreat, you can redesign cities, you can create things that float. And one adaptation strategy that we're going to hear about tonight is standing and staying put and fighting the rising sea. Now, you may remember the story of King Canute, he wanted to show that he had dominion over all things. He had his throne taken down to the edge of the ocean at low tide, and in front of many of his subjects, he commanded the tide to stay out. He was last seen floating out into the North Sea. But engineering solutions will play a major role in this, and it's going to require some of the best engineering minds there are, and we have one of those best engineering minds with us tonight, Brett Sanders from UCI. So we're going to hear from him first, and then we're going to hear from someone who was an engineer and then became a designer, Heidrun Mumper-Drumm. I love that name. Heidrun Mumper. Heidrun Mumper-Drumm, and she's going to talk about how design is important in conveying data and information to the public. It's also important in designing a sustainable future, because the relationships that we have right now are not sustainable, and I will introduce her later. So our first speaker then is Brett Sanders, and Brett is professor at UC Irvine. He's also chair of Civil and Environmental Engineering. He has a BS in engineering from Berkeley, master's and PhD from the University of Michigan, the home state of several of us in this room. And his research relates to a lot dealing with flooding along rivers, managing floods through active floodplain management, mathematical modeling, also coastal and inundation. And his group is now quite involved in dealing with issues along the California coast. And Brett, it's great to have you here this evening.
It's a pleasure to be here. And I just want to sit back and hear Jerry talk some more. You know, he's got so much knowledge about sea level rise and what's going on that I think he could do a fine job of giving this talk as well. But I'll do my best to keep you interested and informed. And if you get out of line, I got a little laser here, so watch out. So my talk is engineering responses to sea level rise and coastal flooding, and as Jerry indicated, you know, my background is in civil and environmental engineering, and traditionally, you know, what's considered the engineering approach has often been the idea that we're going to build a lot of structures and we're going to build strong levees and reservoirs and we're going to control everything. But that's been changing for a while now, and you know, engineers are, you know, thinking about managing risk and recognizing that we define risk in an engineering perspective as basically the product of a probability and an adverse outcome. So if there's a 10% chance that everyone here, that this facility floods, and this facility has like a value of, I don't know, what's a facility worth, Jerry? $2.5, $3 million. Okay, so $3 million, 10% chance of flooding, and then, so there's a risk of, you know, $300,000, right, that on the table. So then we think about that number. We think, well, how could we reduce that risk? Well, we could reduce the sort of the value of the assets that are exposed, or we could try to reduce the probability that it gets exposed. And so it's kind of changed the way we think about managing risk from thinking that we can always protect areas with structures to thinking we need to change the vulnerability of structures. I'll try to bring that flavor to the discussion today, and I hope that gives you a little bit maybe different perspective of what engineering is about. Engineering may not be about building a lot of hard solutions to the problem. It may be about managing a lot of different options. Okay, so I'm going to try to use this little guy here. Next slide. Here we go. Okay, so my talk has some background on sea level rise, and then I'll get into some what I consider adaptation options. Retreat, which is to abandon high-risk areas, protect, armor the shorelines, raise flood walls, and to accommodate, to try to take some steps that sort of modulate the impacts, reduce the impacts, and then hopefully there'll be time afterwards for some discussion. So major effects of sea level rise, you know, on the sort of terrestrial side, you know, erosion, losing beaches, shoreline retreat. There's this book by Pilkey and Young, which called The Rising Sea, which has a wonderful overview of sea level rise to a general audience. And you know, he points out some fallacies that, you know, you take a certain amount of sea level rise and you assume a certain beach slope, and that tells you how far inland things are going to go, just based on pure geometry. But that generally doesn't work. And so everywhere, I think another perspective I'd like you to take from today's talk is that every site needs some careful consideration based on its own geology, its own wave climate, its own topography, and so on. But major effects, so erosion, flooding, And from a flooding perspective, I hope you also leave with this idea that flooding is not going to be a gradual process as sea levels come up and we slowly go underwater. We need to think of the flooding threat as one of an increase in the severity of flood events and an increase in the frequency of flood events. So what we think of the ocean going up and down all the time. And in Southern California, for example, we have flooding events when we see real high tides and waves at the same time. And sometimes we get like a low pressure system that comes in and that builds up the ocean height even more. And we call that a surge, but it's nothing like the surge that you'd see in the Gulf Coast or the Atlantic Coast, which is, tens of feet. We see a surge here of around a foot from a good storm. So we already have tides that go up and down on the order of meters, and we're talking about shifts in the mean sea level on the order of meters. So what we can anticipate then in terms of flooding is more frequent episodes of flooding along the coast. Don't expect the ocean just to gradually move in. Salinity intrusion, another major concern, impacts to the groundwater and the surface water supplies that we rely on. We're concerned about saline water penetrating aquifers in Southern California. We're very concerned about saline water penetrating the Bay Delta because many of the water intakes that supply water to the San Francisco Bay region are in regions that if the ocean comes up, the salt water moves inland, and then you can no longer draw fresh water from the intake point. Habitat loss is another big concern. So as Jerry indicated, if the ocean goes up and down, the shoreline wants to go in and out, the wetlands want to move in and out with the change in sea level, but if we have infrastructure in place that isn't moving, then the habitat has nowhere to go. It loses. Infrastructure loss. We've got a lot of infrastructure along coastlines, sewage systems, power systems, transportation systems. So we need to think about sea level rise up to a couple of meters, 1 to 2 meters. Globally, nations vulnerable to sea level rise are those many of those nations that sit at the outlets of major rivers like Bangladesh, Vietnam, Myanmar. Major displacements of people around the world. Often these low-lying areas. Egypt, of course, is at the outlet of the Nile. Singapore, a very densely developed area that's going to be looking at extensive levee systems to protect the capital. In Indonesia, airports projected to be inundated, city projected to be gone in 2050. There's been discussion about moving the capital inland. Many of the Pacific Islands are a threat. I imagine you've heard some of this already in previous talks, but I thought it's helpful just to kind of have a little bit of a global perspective. This slide, worked by Hansen, kind of looks at the exposure of populations around the world. These green bars in the bottom are kind of today's present-day exposure. And the U.S. is up there in terms of how much of the population is presently exposed. But with this is exposure to coastal flooding and hazards. And so there's two drivers here of an increased exposure. So 2 additional increments on these bars. So one of these increments is sort of the climate change, right? This is the top bit. But the other bar is what's called socioeconomic change. So anybody want to wager a guess as to what that means? So why is the population going to be more and more exposed to hazards because of socioeconomic changes? Yeah?
Either more people or more people near the beach.
Right.
People with money buy property where they shouldn't.
Mm-hmm. So this is a trend in people moving to coastlines. There's a major trend around the world of people moving to urban centers. Increasingly, those urban centers are on coastlines. So a big part of the increase in sort of future population at risk is just people moving. It's not even the sort of the climate-driven factor. I think that's important to recognize, and that's something that presumably we can play a role in shaping that through policies and so forth. So globally, these are the most vulnerable cities, according to a table published by Orrin Pilkey. Number one on the list is in 2 and 3 are all U.S. cities. So the United States is right in the middle of this coastal flooding, sea level rise problem. Japan has a couple cities on the list. Amsterdam sits below sea level, protected by major levees. Rotterdam. In the U.S., so anybody want to wager guesses other cities in the U.S. that are at risk of flooding? If we did the top 10 cities in the U.S. vulnerable to coastal flooding, sea level rise. Southern California is maybe up there, yeah? San Francisco. So we got to think nationally in terms of major metropolitan areas. So we'll put Los Angeles in there for some major metropolitan area. We'll put the San Francisco metropolitan area. Any other major metropolitan areas think might be at risk? Let's look at the New York is Tampa, Virginia Beach, Boston, Philadelphia, San Francisco, Oakland. These are ranked as well, a ranked list. So some of our most populous cities are on the top of the list for being vulnerable to sea level rise. Yeah, this would be sort of your major, if you looked at major metropolitan areas, yeah. Seal Beach would be considered part of the Los Angeles region. And this table here looks at, okay, we've got these sort of areas at risk, but who can afford to do anything about it? So excuse me. I can't stop it. Embarrassing. I'm so tech. Oh, yeah. I think it's pizza night at UCI. $5 pizzas at the Steelhead. So here we have countries and their ability to sort of go after this and address the problem. So China, top of the list in terms of population exposed. The characterization here by Hansen and coworkers is that they're going to be able to afford to construct defenses, probably not to a uniformly high standard, but they're going to have resources to protect cities. U.S. is considered, a country that's wealthy and able to afford to construct, high-level defenses. India has, millions of people exposed, but their resources per capita are low, and so they're not expected to have the kind of resources you'd need to defend to sea level. And that's kind of the way this table goes. So Japan has resources. Vietnam, very vulnerable, but not the resources. Netherlands, high levels of resources. Bangladesh, low levels of resources. Egypt, Thailand, and Indonesia are characterized at an intermediate level. So able to afford to construct defenses, but not to a uniform high standard.
I'm surprised you don't have Taiwan.
Yeah, I don't know. Jerry, do you know what Taiwan's situation is relative to sea level rise?
This is also population.
Yeah.
Population
Mm-hmm. So this little review I hoped would sort of help you recognize that sea level rise is a major issue facing cities in particular. In cities, we find that both cultural and economic assets are clustered. In cities, we find resources for infrastructure. In city, there's political capital to get things done. But we have to recognize that the built environment is a barrier to change. So naturally, shorelines want to migrate. They want to move up and down with changes in sea levels, but the cities are going to try to stop that. And so that creates a tension where the natural environment's trying to move and the cities are trying to stay in one spot, and that's where we face erosion problems. Local sea level rise is very important. Sea level rise here is not the same as sea level rise in San Diego, if you look at the last 50 years of data, or San Francisco. There's little differences. Okay, so why aren't they the same? Did you talk in some of your other classes about globally, even if you look at absolute sea level rises, how it's not all the same? Actually, Jerry mentioned earlier about California's sea level rise has been suppressed the last couple decades due to this Pacific Decadal Oscillation. So wind plays a role. So ocean levels, first of all, are variable. But as Jerry mentioned, that we can think of absolute ocean levels changing relative to some fixed datum in response to more water in the oceans. They can respond to shrinking space for water depending on how the geometry of the ocean basin changes and the expansion of water with temperature. But local sea level rise is the difference between an absolute sea level rise and a change in what? Has something to do with the land, right? So the land heights aren't the same everywhere. So land might be going up, might be going down. What do you think happening to land near river outlets? River deltas? Going down. So why is it going down? Subsidence. This is a well-informed class. We can sit back. So we've got areas like deltas where we've got subsidence, and so the land is going down. What else makes the land go down?
But it's not going down in Palos Verdes, is it? Isn't Palos Verdes rising?
I don't know the local geology at Palos Verdes. I can't answer that.
PV rise is about an inch a year.
So, but things like oil and gas exploration can make a big difference on local land heights. So we've got groundwater changing with subsidence, groundwater extraction can pull the ground down, oil and gas exploration, compaction of soils, and earthquakes. In Japan, major earthquake, there's areas now that are being flooded by high tides every day. The land shifted down by several feet, and now it sits at a lower elevation, and some of the coastal topography is being flooded. So sea level rise then should be viewed locally. If you're thinking about adaptation, what is the sea level rise rate here where I live? And that gets at both the overall ocean level change and the local changes in the ground level. So cities need to plan according to local rates. So adaptation options, where I hope we'll be able to chat about a few things. We can retreat and relocate, give up ground. There's a number of different sort of maybe more traditional engineering approaches, which is to armor the shoreline with things like breakwaters, revetments, and groins. We can try to raise the shoreline with levees, floodgates, try to build a perimeter of higher elevation that holds back water. We can try to nourish the beaches, keep the beaches with lots of sand on them so that they provide protection. Or we can accommodate the flooding, trying to find sort of some intermediate solution that limits the impacts of sea level rise. So these three in the middle can be thought of as sort of protecting, and this can be thought of as accommodating. So in your mind, you can think, well, we can retreat, we can protect, or we can try to accommodate some of that change. So retreat and relocate. I'll try to share a few examples of how this has maybe been done in the past, or how it's happened in the past. And this does sometimes make financial sense. For example, along the major rivers of the US, there's been cities that have been picked up and moved on top of hills nearby because the flood risk along the river was too high. Pardon?
You know the temple of Abu Simbel in Egypt? They moved the whole temple because they were going to flood the, what is it, that dam up there?
Aswan High Dam, yeah. But cities have been flooded in the past, and people have abandoned them. And a few examples of Alexandria, Egypt, thousands of years ago. It's thought that it was catastrophically flooded by an earthquake that lowered the land height by many feet. Apparently there were several cities along the Mediterranean that all appeared to have failed at the same time, leaving the cities behind underwater. In the 1600s, there was a major port in Jamaica called Port Royal. Again, during an earthquake, fell into the ocean, land lowered, over 5,000 people reportedly were killed. So here we see a scuba diver exploring the remains of the city underwater. On the Gulf Coast and East Coast, there are many towns that have been abandoned. Often these were small towns built on barrier islands with hundreds of homes typically, and they get destroyed by hurricanes, and so folks walked away. So like lost in Louisiana, South Carolina, North Carolina, New Jersey. One of the more recent examples of a major development sort of just being left behind was in the Brownwood subdivision in Baytown, Texas, which is sort of in the greater Houston area. This is a neighborhood of over 3,000 homes built into the 1970s. And what's going on in Houston? Oh yeah, oil business, right? And also, groundwater extraction. So the land there dropped 8 feet from 1951 to around the present day. And that put this town at higher and higher flood risk every year. They were exposed to flooding during some hurricanes, and it was abandoned. So now here we have Google Maps. It's kind of crazy, but they still got the old streets on there. Nobody lives there anymore. People walked away and left behind homes like these that are now a wetland. So this house doesn't look too different from houses you might see in Southern California, a wood-framed home built in the 40s, 50s, 60s. So it happens. Communities, there are examples of people walking away from communities. In this case, FEMA played a role in helping those people relocate. So retreat and relocate, my point is that there are examples of this happening in the past. And I think our first reaction is that we never do that. Well, I think in some areas that are very, very well developed and have the resources, and it makes a lot of sense for them to stay there, we will fight to sort of maintain them. But there are going to be examples where we walk away. And the policies are changing the USA to facilitate this option. After Katrina, there were communities along the Gulf Coast, on the mainland, that were not rebuilt because it didn't make sense. So sense is starting to enter the picture from a flood risk management perspective. So option 2 is armoring the shoreline. So I thought it would make sense to kind of understand some of these coastal armoring ideas, coastal protection ideas, to just get a basic overview of coastal processes. So I'm going to give you a overview of some important processes that are relevant to coastlines. First, this is an aerial shot of a major river delta. Does somebody want to tell me what that is? Yeah, Nile River Delta. Okay, so So rivers deliver both water and sediment to the coast, many other nutrients as well. And as we've dammed rivers, this has blocked the supply of sediments to the coastlines. And those sediments are important for maintaining beaches. So we rely on terrestrial processes to shed sediment, rivers to bring it down to coastlines, and then for waves to redistribute that sand along beaches. And when you reduce the supply of sand, then the waves keep pushing sand down the coastline, but there's not another supply mechanism, and so beaches get smaller. So we've had deficits of beach sand from blocking rivers with dams. Something else we do in these deltas is we tend to channelize the flow. So naturally, a river delta like this one will want to take different path every year, spread out and fan out, and water is going to want to go different directions. But that's not good for transportation. If we need to move goods up and down rivers from between ports, then we need to be able to have channels in here. And once we channelize these deltas, then we need to have facilities along the deltas to load and unload the boats. And so we need to put infrastructure, and then it's kind of a process where more and more infrastructure gets in harm's way. But I guess relative to coastal processes, the important point here is that the channeling of the rivers stops the natural deposition processes that build up coastal topography. So we're not seeing the deposition of soils that build up the land once we channelize the rivers. A little bit about wave dynamics. This is a nice little picture, I believe, in the San Francisco Bay Delta, showing how waves coming through a restriction here fan out in nice arc-shaped structures, and that is called wave diffraction. You studied, in physics, you may have taken an optics class and learned about diffraction. So diffraction is the bending of waves around corners. So waves come through here, and then they want to curve to the side. There's another process that causes the waves to curve and change direction, and that is called refraction. And refraction is caused by changes in the depth. So when waves encounter shallower water, they slow down. And so that sort of difference in speed between offshore, a wave's going faster, closer to shoreline where it's shallower, the wave goes slower. So that's going to cause the wave to kind of turn towards the shoreline. That's what we call diffraction. And then reflection of the wave is the reversal of the wave direction when it hits like a solid object, like a wall or a shoreline. Okay. So armored shorelines, we have to bear in mind, are going to reflect more energy than beaches, which tends to eventually push the energy somewhere else. And we'll come back to that. But I wanted to have a little basic understanding of how waves move through coastal topography, particularly because of this point here, getting back to sediment. We talked about rivers delivering the sediment to the shoreline. The waves are responsible for redistributing that sediment up and down the coastline. And there's something called Longshore Drift, which is the shoreline movement, a longshore movement of sediment. And that's driven by these waves. So a wave field comes in, it's curved to the shoreline, and we call that what? Refraction, right? Refraction based on the shallower depths. And then when the wave hits the beach, it runs up, it runs back down, and we've all put our toes in the sand, and we felt that sand move under our feet. And it's always remarkable to me when I go to a beach and I put my feet on the sand and I feel that sediment moving, how much that sediment's moving is remarkable. You can find that holes are dug around your feet as you stand in the sand and you feel that sediment moving. So it's a remarkably active process. But when the waves come at an angle, the waves run up at an angle, and they'll often run straight back down the beach. And so that causes a net movement of sand down the shoreline. So what this arrow is showing is the waves run up and then back down, up and back down. And there's a progression of movement in one direction. That's called longshore drift. Okay? And this little photograph shows what happens when there's longshore drift along a shoreline and that landmass stops. See that? So imagine this, the major landmass here is stopped. But what's happened? Where did that come from? Why did it stick out there? Well, it's because there's this river of sediment coming down the shoreline, and it just keeps on going, and it builds up and it creates what's called a spit. Okay? So we see that these wave-driven processes are responsible for reshaping the shoreline and moving sediment around. Yeah, do you have a question? This takes years to decades. In Southern California, these types of spits are now very developed. Newport Peninsula, for example, was a spit just like this one, and it was built up. And now it's nourished to maintain its height. I need to keep moving along here. So beaches also go through seasonal adjustments where you may notice in the summertime the beach is nice and wide, in the wintertime the beach gets small. That's a natural process of beaches changing shape. And the beach, nice big beach that builds up in the summer, in many ways is sort of preparing for the winter. It's preparing for the big storms that are going to come with the big waves that are going to erode the beach. But then that sand just moves offshore, and then the summertime comes along again, and the sand gets moved onshore again. So beaches naturally change size. We need a little bit of room for beaches to go in and out each year. In some cases, as sea levels rise, what will happen is just the beach is going to want to translate. So here we have a beach initially, sometime later it just translated to the side. And that can happen through a sea level rise process, or just even if with constant sea levels. This can happen on barrier islands in particular. Overwash fans are interesting. When big storms come, they'll dump sediment to the backside of what we call the backshore of a coastline and move material inland. And when we have big storms and we have people on offshore barrier islands, then those places are exposed to a lot of damage. And this is called Dauphin Island in Alabama that was wiped out by Katrina. So armoring options, that's just background in coastal processes. Now I can share with you some armoring options. Groins, jetties, offshore breakwaters, seawalls, some revetments. These are things we can do to try to shape the coastline in order to protect valuable infrastructure from damage, and sometimes to create navigable waters as well. So groins are structures that are built perpendicular to the shoreline. So we start off with a beach that's been eroded, and we'd like to kind of bring sediment back to that beach. And so by putting groins in this longshore transport, remember we've got the waves moving sediment, we're putting these barriers opposite to the transport of the sediment. And the idea is we're going to catch some of that sediment as it moves down the coastline. And so the sediment is caught by the groins, and the beach grows out. And successful groin fields will see the beach widen, and eventually the beach profile can get quite thicker. This is a successful groin field that was installed in West Newport, south of here. This coastline, the beach had narrowed and was nearly on top of the houses back in the 70s, I believe. And since that time, the beach has been restored. I believe that's a permanent feature of the coastline, this groin field. There's another example of a groin field. You can tell which way the waves are coming. You can see the wave fields on top here, and the way that the sort of the half-moon shape here of the beach is angled always in the upstream direction. Jetties are like groins, but they sit at the outlets of channels, and these promote a deep water channel, so boats can go in and out of harbors, but they also can be used to promote accretion at a beach. So here again, we're blocking longshore transport, and all the sediment builds up on one side. On the other side, do you want to be there? So what we'll find with most coastal structures, most armoring options, they they're attractive in one regard, but they have a downside as well. So why is this beach so small now? It's so small because we've starved it of sediment, right? So the waves are still going to be coming. They're going to be coming. They're going to be grabbing sediment and moving it down the coastline. But that supply of sediment isn't there anymore. So it's like you've got to take a water, and it's got water going out, but nothing coming in. So the tank gets emptier and emptier. Offshore breakwaters, we have one offshore of Long Beach. These reduce wave energy striking a beach. And when we reduce the wave energy striking a beach, then sediments are less likely to move in that area, so they accumulate. If they come into the area, they deposit. So breakwaters are used to protect harbors from damaging waves. They unfortunately restrict circulation, so one of the downsides to breakwaters is that you've got a region of coastal water which isn't as circulating as well as it was before, because you don't have the waves and the currents flowing through that area. And structures like these will reflect wave energy. And when wave energy hits here and reflects off, it doesn't just go off to sea. The wave energy wants to curve back to the shoreline. So that wave energy is going to hit somewhere on the shoreline. It'll be distributed. It'll be sort of diffused. But it does mean that the other parts of the coastline will receive more wave energy than if that structure wasn't there in the first place. And that will change the erosional nature of the shoreline. Seawalls. Here we see a sheet pile type seawall protecting some homes along a beach. And these are often used on the open coast to protect the upland areas from erosion. We also see them in harbors and inland waterways because you can dock your boat along something like that and so forth. But the downside to the seawall, so we put the seawall in, we have a beach here, is that we tend to accelerate the rate at which this beach is eroded and quickly lose the beach. And what happens here is that when a storm comes along, instead of the wave running up all the way and dissipating its energy, it hits that wall and it reflects off, and there's a lot of energy in that fluid, a lot of turbulence in the fluid, which keeps the sediment in suspension. And so there tends to be a stronger offshore motion of the sediment. There's actually a feedback mechanism that comes into play as well, is once the sediment gets lowered, and when the waves come in, they're breaking closer and closer to the wall. And so they even become more and more erosive because more energy is getting closer to the shoreline. So there's a negative sort of, or a feedback mechanism here which tends to accelerate erosion once that wall goes in. Whoops. Here we go. So revetments. Revetments are slopes of riprap, or in this case, there's been some engineered riprap. These are called Ajax. Like jacks when you were a kid, you played jacks, and we'll play on that. But this is a Japanese coastline that's been armored to guard against coastal erosion. Beach is gone. No longer have a beach there. So revetments are sort of sloping structures designed for erosion control. They dissipate more energy than seawalls, so that's good. They're dissipating some of that energy instead of reflecting so much of it, but they tend to increase erosion elsewhere. And the aesthetic value is really poor. So let me skip past this because I talked about that. So summary of armoring the shoreline. Armoring is really necessary for meeting basic infrastructure needs of coastlines. Ports, beaches, wetlands, in a stable climate, assuming no significant changes in sea levels. But you're not going to keep pace with 1 to 2 meters of shoreline with riprap and groins and so forth. And this is not the answer to major sea level rise. So let's think about another option, raising the shoreline. We're talking about major levees in this case, floodgates and so forth. And we'll see a few examples of systems where the idea is to create gates that can be open most of the time. That means the normal tidal flows in and out of estuaries can proceed. But in the event that there's a major threatening storm of some type, we can shut those gates down and then protect the infrastructure during those times. And so the Dutch sea defenses are sort of an example of that. These are the gates that protect Rotterdam, and these are the gates that protect areas further to the east. And these are the example of the Dutch levees. The Thames barrier in London, maybe some of you have seen this. This is a barrier that again, can be raised if there's a strong surge in the North Sea that comes up the Thames estuary. And then otherwise, you can lower the gates and vessel traffic can move in and out of the estuary.
Wasn't London on that list? I mean, London has a huge flooding problem.
Yes, they do. Yeah,
They may lose the whole city.
that's true. And major resources go into building these facilities. This is for Venice. This is called the Meuse system that's going into place, where they're putting these gates, these are called flaps actually, at the outlets or between the islands, so that they can again stop the progression of a large tide into the Venice Lagoon, which is this region here. And so they're trying to keep the height of the sea well above the height of the lagoon. Very expensive systems. This is a photograph of New Orleans levees. Doesn't seem to convey quite the same, panache or whatever of the. Look at these nice systems. We go to this one, and of course the Sacramento San Joaquin Delta levees. You may have heard by now that these are often very vulnerable to failure. So raising the shoreline is an option for sea level rise. It's an option that's already being used around the North Sea. Venice has decided to go with that option. And the idea is to try to have a facility that you can use every once in a while when these threatening conditions exist. Otherwise, can support some of the other important functions of coastal waters, like you want to have good circulation for water quality and habitat and so forth. But there's a major problem with levees and tide gates and major engineering structures is that they create a very false sense of security that promotes a lot of investment in high-risk areas. So, and this is a story that's been told over and over again along major rivers. The big structure goes in, people feel safe, people invest more resources in infrastructure, facilities, and that sets the stage for flooding disasters. These facilities are also very expensive. Beach nourishment is another option. This is an example of spreading sand, pumping sand up onto the beach. And beach nourishment is in widespread use today, especially along Florida. We use it here in Southern California at our beaches. Enhances a very natural buffer to flooding and erosion, which is beaches. I think the real attractive aspect of beach nourishment is that we're trying to enhance something that's much more natural than a hardened structure. But the adverse impacts are things like disruption of the soils, increased turbidity of coastal waters. You can get sedimentation down onto coastal reefs and so forth. They also require high-level maintenance. But beach nourishment has some appeal. Accommodation. These are the intermediate solutions we should be thinking about. Galveston, Texas was wiped out by a hurricane in the early 1900s. They raised the city 5 meters. Soil was brought in, the ground level was raised up, major church in town was put on jacks and raised up. Homes were raised up to a higher elevation, soil was pumped in, and that is viewed as a success in terms of mitigating future damages. So grade raising, something to consider.
Some are on stilts too.
Yes,
Still on stilts.
right. Water injection. This was an idea in an area that was threatened. Wells were built, water was pumped into the ground, and over time, as the pressure in the water went up, the height of the ground came up. And so in this case, this experiment was done, and over a period of 3 or 4 years, the water was pumped in, the ground level came up 7 centimeters. pumps were turned off, and that didn't have a lasting effect. Okay, so it was not a solution that could be walked away from. I suppose you could keep the pumps running and maintain a higher ground level. But here's another idea that's been being promoted by a colleague of mine at Clemson University called mudjacking. No relation to carjacking. Mudjacking is a process by which you take a site like this one, say some buildings are on top, you put wells down into the ground, and you send into the ground through wells a combination of liquid and solid. You create a slurry. And that slurry starts injecting into a layer in the subsurface, and you start growing that layer by pumping more and more of this slurry in there. And that slowly lifts up the ground. This is an example that was done again in Italy, where at a test site they got 10 centimeters of lift, roughly, a little over 9. They turned off the pumps and they sustained that height. So unlike the water pumping, which quickly went down again, the mudjacking retained its elevation. This is now being explored in Germany. Look, they've got like a whole sea on this plot of land that they're thinking we're going to mudjack this site up. And you can see examples of wells going into the ground, building up that site. They've got roads and churches and everything there. They're going my colleague Larry Murdoch at Clemson did a sort of cost estimate of mudjacking New Orleans. And first of all, he looked at sort of the cost of repairing levee damage from Katrina, around $14 billion. They've got a plan to protect the coastline. It's going to cost, say, $5 to $17 billion. The Dutch spent around $15 billion. He seems to think that you can get up to 10 meters of lift in New Orleans with around $5 billion. Something to think about. Flood resiliency. This is another aspect of sort of adaptation. And this is what mentioned earlier about building higher. We could put our assets out of harm's way. Pardon? Yeah. Well, you know what? And a part of that also is early warning systems. They're going to be something else we talk about. Flood forecasting. If research has shown that if you have a couple of hours lead time from a major disaster, you can reduce your losses by up to 40 to 50%. You take your valuable assets, you get them out of harm's way, and what's left is less is lost because the most valuable things you've moved. So flood forecasting is, in flood prediction, is an important part of the picture, and that's where we've been doing work. This is a system that the USGS is trying to put together to take their stage data and notify people about flood zones and who's going to be impacted by floods. And this is work we're doing here in Newport Beach, where we're trying to build models that we can use to predict localized flooding. One of our perspectives is that a lot of the flood mapping is done at relatively coarse resolutions that people don't find believable. And if you look at flooding, especially in urban areas, it's very localized. Water snakes up streets and so forth. So we're trying to build models that depict flooding in a way that's consistent with the way people experience it when they're in cities. And we have digital models of, this is Balboa Island in Newport Beach area. We find that it's very important that we get in there, and these are a flood wall that goes around the island. We've surveyed that very carefully in order to accurately depict the height of that, because if you don't get the height of that wall right, you can't predict flooding right. You have to predict the onset of overtopping in order to predict flooding. So we use aerial LiDAR to measure the heights of the land surface, which is a scanning technique with an aircraft. And we use Magellan, I was talking earlier about technology, survey instrument to get this wall heights down more accurately. And then we found that this is a prediction of flooding from an event that took place in 2005. The green areas are areas that we correctly predicted, and we did pretty well. There's areas of over-prediction where we predict flooding that didn't happen, and areas of under-prediction where flooding happened that we didn't predict it correctly. But we're finding with our models we're doing much better than some of the other models that are being used, which are overly simplistic because they don't consider the details of the walls and the flooding mechanisms, the hydraulic mechanisms that allow water to move from the bay into the islands. So in summary, on this accommodation slide is that the idea is to get infrastructure moved out of harm's way. And this is attractive, more attractive, I think, than some of the levee scenarios because you really do get the risk of flooding goes away. It's been done before. Things like grade raising have been done. Mudjacking is attractive. It's not going to work everywhere. It requires certain types of soils, but it's an idea that has some merit. Promoting flood resilience and preparedness through mapping and forecasting is also important. We were having a dinner conversation earlier about how important it is just to communicate flood information to people so they can take ownership of the problem and make decisions locally that will have a big effect when you think about it, the impacts community-wide. So my summary is that sea level rise should be approached with a local mindset, identify the local sea level rises. We can begin preparing now. We can map high-risk areas. We can forecast flood zones to enhance preparedness. We can implement flood-resilient building and land use policies now. And when you get into coastal engineering solutions, they're all going to come with trade-offs. There's not going to be a panacea out there that's going to, this is going to work best for you. But whatever's best will also depend on public values. How much do people value beaches versus transportation and so forth. So I'd like to thank the Aquarium for inviting me here and the chance to visit with all of you. My student, Timo Glean, helped me a lot with getting my slides together. And Jochen Schubert, one of my postdocs. So
thank you very much for Jerry for inviting me to come speak to you tonight. I hope I can tell you a little bit of what the role of the designer is, given the changes that are taking place in the world. So I want to start with kind of a big picture view and kind of pose this phrase to you: the future looks different. I think we can all agree on that, no matter where we are on the global warming discussions, the lack of dialogue thereof. But we can all certainly agree that the future is different than the world we are experiencing today. And I'm going to talk to you about what designers are doing to prepare us for this world that is different. I've divided my talk into two sections. So we're going to do the future is different part 1 first, in which I'd like to just kind of briefly tell you what we're doing on the education side to enable designers to design for this different future. Then I'm going to speak to you about the role of the designer as a communicator of scientific information, which we know is very, very important and which is not happening as easily as we would like. And then I will go quickly into the project that we just finished with Jerry at Art Center, in which our studio class was tasked with imagining what sea level rise looked like and what do people need to know about sea level rise. So we're going to do part 1 and part 2. So part 1, future looks different. What are some of the things we can agree on? Well, we all recognize that climate change is taking place and it is being accelerated by an enhanced greenhouse effect. We can all agree that resources are being depleted. We all know that our resources are finite. We're not going to get more stuff. Whatever stuff we have is already on the planet. unless you count maybe a few meteors hitting the Earth. But for the most part, what we have is what we have to work with, and we're using those things up at an ever-increasing rate. This climate change in combination with depleting resources is stressing our ecosystems and the organisms that live in those ecosystems. And then to top it off, we have population growth. This is the number that the CIA came up with in 2008. It turns out that they take the most accurate population data. And we also know that by 2040, certainly by 2050, we're looking at between 8 or 9 billion people on the planet. So that's the future, that's the different future that we see out there. So that leads us to these two strategies. We can either mitigate, we can try to undo some of those impacts, or we have to, in many cases, adapt to this changing future. Hence the role of the designer. The designer is tasked with developing mitigation and adaptation strategies. And so to Jerry's point, it will be a future by design. How is this being taught in the schools that teach design? Well, I can talk about Art Center College of Design, and I can tell you that there's still a big split in how design is taught. We have traditional design that uses the form plus function definition of design. I'm sure you all have heard that. Design is form and function. And sustainability or sustainable design is viewed as some kind of weird design. It's usually made out of hemp. It's made out of brown paper, it's craft, it has soy ink. Sustainable design is some weird design, and the real design is this form function stuff. And that is still true. What we're trying to do is redefine design, take a more comprehensive look at design, and integrate sustainability as an attribute of design. Now, this seems like a very simple approach, but it's very fundamental to how designers think and how design is taught. Unless we integrate sustainability as an attribute, this comprehensive approach to design is not going to happen. You're still going to get the weird sustainable design and then all the other stuff. So this is what we're trying to do slowly at Art Center, and many of the other art and design schools are on a similar path. What we'd like to see is ultimately design is form, function, and sustainability. Sustainability is a priority along with form and function. It's really, really critical. Another thing we're doing is we're teaching the designer a new language, a new metric, and a new methodology. The designer needs to know more. If you're going to do comprehensive design, you need more information. By new language, and here I like to use the brain. That's the brain of the designer, envisioning this beautiful Thames chair, if you're familiar with that. What is the new language that the designer needs to speak? Well, they need to understand things like carrying capacity and biodiversity and PBTs and the Brundtland definition of sustainability, which I'm sure you're all familiar with. They need to know about the 3 E's and ozone depletion and triple bottom line and risk assessment. These are not languages or concepts that the designer was usually taught. They now need to know this in order to integrate sustainability into the design. So we're teaching this new language. We're also teaching a new metric. The metric of design was, well, does it look good and does it work? Well, now it also needs what's its carbon footprint? What is its eco footprint? Does it conform to ISO standards? Does it use natural capital? Is it LEED certified, FSC certified? What about sustainability report cards? Design is now going to be measured. You're going to calculate a score for whether design meets certain criteria. That is also very, very new for design. Designers worried about, again, what does it look like? What is it going to retail for? Those were the kinds of metrics. There's a whole new set of metrics that the designer must learn. And a new methodology, which is life cycle assessment or life cycle analysis. The designer needs to understand the entire life cycle of the product or system that they're designing. And just briefly, I have side by side the traditional design process and the life cycle design process, which front loads the design activity with lots and lots of research, including a life cycle assessment of what product or system you're going to be designing. And from that, you're going to create goals for your design. Your goal isn't just going to be make it look good and make sure it works, but does it reduce impacts in critical areas as shown by virtue of your life cycle assessment? You're going to do a life cycle assessment, you're going to understand where the potential negative impacts are, and you're going to set your goals to try to minimize or eliminate those impacts. And that is what is supposed to drive design. This I just want to show you. This is part of a life cycle assessment. It's called the process tree. So this was for a set of headphones, and it traces and tracks all the material and energy flows that go into making that headphone, making, using, and disposing of that headphone. So you have your raw materials, you have your different manufacturing steps. You also list what other materials are input at every step and what outputs occur at every step. Because you're trying to really understand the life cycle impact of your design. And ultimately, we are trying to kind of coach our students into allowing this information to really determine what their design goals are. Now, I'm going to give you a quick set of examples of, well, what kind of products do you get by using this method? So here's an iron. Say you're told design an iron. And I like to use half the brain. They're not using their sustainability portion of their brain. This is just form and function design. So using a conventional design process, you'd get a form and function iron. The focus was very narrow. It just looked at functionality and form. What if you use some life cycle assessment in your design work? Well, now you're using your whole brain, and this is the kind of iron that a student designed. It was designed to minimize impacts that were uncovered as a result of the life cycle assessment. And just in more detail, he designed it to be disassembled and materials reharvested at the end of its life. So it actually came flat packed. So the user had to assemble it so they would know how to disassemble it when they no longer wanted to use the iron. What's interesting is you get an entirely new aesthetic. The student didn't set out to design a transparent iron. The student set out to design an iron that minimized environmental impacts and got a completely different look to the product. Conventional blow dryer. Say you need to design a blow dryer. This is what you get. This was the blow dryer we got using life cycle assessment as part of the process. Took away the plastic shield completely and relied on the mica, which is really what is the functional part of the iron on the outside. Skim board with all the foam and the different layers in it. What does it look like if you use life cycle assessment or design using life cycle assessment? The eco deck, in which the structure actually became an aesthetic feature of the skimboard itself, and the transparency of the material gave it a completely different look. He actually wanted to design a completely clear skimboard. He thought it looked really great. The thing is, he took it down the beach, and he couldn't find it. So then he realized, okay, I'm going to have to color this thing. So the tint came as part of the functionality. Typical fan. This is what a fan looks like once you take it through this life cycle process. Mattress, one of the worst products. Just try throwing a mattress away and you'll find how difficult it is. This is a mattress. Considering the impacts of a typical mattress, this was redesigned where there was no commingling of materials. They were all, you could take layers apart, you could wash them. He ended up creating a support system out of plywood, cut plywood, and without even realizing it, he eliminated the bed frame. So he got rid of a whole other big component. He also was able to sequester that frame together, so now the person could take the mattress home in their car, and you didn't have to rely on a delivery truck that maybe had 1 or 2 mattresses in it, burning a lot of carbon, adding to those greenhouse gases. You could take this home in your car, and if you ordered, say, a twin size and then you wanted to make it bigger, you could actually add additional components to it, or you could break one up and make it smaller. So a really beautiful project. This actually won an IDSA Bronze Award just this year. Fire extinguisher, that's what it looks like when you include sustainability. Again, the aesthetic changes just because you're paying attention to your life cycle goals. IV unit, scary thing. You don't want to wake up with one of those next to your bed, right? Makes you feel sick just looking at it. This was another IV unit, eliminated polyvinyl chloride, was still on rollers, had a nice little green light that said the IV bag was full. Students have even tackled things like, this is a system of burning joss paper that's used in Taiwan. We looked at that ritual and took it through a life cycle assessment. We also did some chemical analysis and found that there was zinc and barium in the paper. So that immediately became a goal for the redesign. She wanted to eliminate those sources and redesigned it. Students have tackled mobility. This is a system for women in rural India. This student designed a desalination system. This is a typical one. He actually did one that was supposed to float outside here in Long Beach Harbor. And Joel did a wonderful burial rite where you put the body within almost like an acid bath, and it decomposes within 4 hours. And you mix that with soil, and then he had a kind of a park scheme where you could bury this soil within a park. So none of this mahogany with brass handles put into a concrete liner, unsustainable burial ritual that we have now. He came up with this new, I told him I volunteered to be the first user. So that was the Future Looks Different Part 1, in which designers are being told and taught, you need to think big picture, you need to understand the language of sustainability, the metrics by which it will be measured, and the methodology is life cycle assessment. The future looks different too. I want to kind of remind you of what we said about population growth. And also remind you that we agreed that it's warming, it's us, it's fast, it's dangerous. What the modelers can't tell us, however, is what will the humans do? Modelers can do a great job of trying to create scenarios, future scenarios. What happens if we release this much stuff? What happens if we replace this with that? What they can't model very well is our behavior. What will the humans do? And that's something I want to talk to you a little bit about, because I have a pet theory as to why we can't predict what humans will do. So this slide, I put it up there to kind of illustrate this imaginary meeting that I'd like to put to you. Imagine you're at an intersection, and here come scientists, and they have wheelbarrows full of scientific data. They're struggling because they have so much scientific data to share and to give us, and that support the various scenarios of global warming and climate change. Okay? The data is credible, it's been peer-reviewed, the IPCC has published consensus reports, there's 90% probability that it's human-induced. There's agreement in the scientific community about what the future will look like. So at this intersection, we've got the scientists with all their data. Now come you and I. Here comes the public and the policymakers. And we bring questions and good intentions. And we start talking, and you see this going on, right? But it's a dialogue of the deaf. Neither side can speak to each other because we don't talk the same language. Again, lots of hand waving, lots of hand gestures, but no real transfer of information is happening. And I think that's a critical problem. So I did a little bit of reading and research, and came up with some ideas as to what designers can do to assist scientists in translating this information to the public. Because I really believe if we understood what was going on, we'd know what to do. It wouldn't be a question of what will the humans do. The humans will do what needs to be done if they understand what needs to be done. So number one, rule number one, know your audience. Sounds very simple, but we forget it all the time. Know what flock you're talking to. Do the scientists, are they speaking to children? Are they speaking to adults? Are they speaking to educators? Are they speaking to the public? They need to tweak their message or translate their message in an appropriate way. I was saying at dinner today before today's talk that virtually every version of the hockey stick graph that shows temperature rise and CO2 emissions, that's the same chart that was in the scientific journals. And it's in Al Gore's film, it's in every reproduction on, or booklet on global warming. Do people really understand what they're looking at? Is there a better way to depict that information? The first thing you need to do is know who you're speaking to and design accordingly. Know your media. We don't just use print now, there's all kinds of other media. Where do people get their news? Do they hear it on the radio? Do they watch a TV program? Do they read it in print? Do they go to their favorite online site? The scientific information needs to exist on all of these various platforms. Does it need to be we said today at dinner too, does it need to be an app for an iPhone? Scientists need to take advantage of all the various media that are available today. Now, this is something that I was never in favor of. I tend to be a little more analytical, but over time I've really found that this is a good strategy. You can't just give the data, you have to tell a story. You have to, people, they're drawn in by a narrative. And scientists they don't tell stories. They give you information. They give you data. They provide facts. Well, somehow that needs to be put into a narrative of some kind that makes it more accessible to the public. Layer the information. We need to clarify information but not oversimplify. And the analogy I have in my mind is, think of the information transfer like a tree. There's some people that just want the trunk's worth, the basic, just give me the basic information about a topic. But there are others that want to understand the limbs and the twigs and the leaves. They want to go deeper. You need, or the scientists need, to provide information for all of those levels of learning that people might want to access. Don't just stop at the trunk. Go deeper and wider. Activism. More and more community groups, campaigns, even online news groups. Scientists, or the science must live in these worlds as well. So let me kind of summarize this. The designers know how to visualize knowledge. The scientists need to tap into that kind of skill set, because that knowledge that they have needs to be translated to the people that need to understand it, the rest of us. In addition to visualizing the knowledge, create a story around it. Tell a narrative. Tell me why it's important. Don't just tell me. Tell me why it's important and why it's important to me, and provide the context. Let people know that, it's about you, but it's also about the rest of the world. These are kind of 3 critical steps, critical layers that should be in the information transfer. So again, to summarize, in my mind, we're trying to provide for the ability to think about the future so that we can guide our present actions. That's really what we're trying to do. We want to be able to think about the future so I know what to do now. And with that, I'm going to move right into an application of this sort of approach with a project that Jerry brought to Art Center.
Can I interrupt?
Yes.
I want to tell a story that relates to disposition. Since a number of us are from Michigan and Detroit, I have to tell you.
Is this sustainable?
Well, you'll have to decide whether it's sustainable. I lived in Detroit, and Detroit is the only city in the world, I think, where if their professional sports teams win, they riot. If they lose, they have a riot. It's an equal opportunity rioting city. And they like to tell a story in Detroit. This guy died, and so they put him in his best suit. They put a top hat on, put a stogie in his mouth, put him in his favorite car, big, long, black Cadillac. They dug a big enough grave to accommodate the car and everything. They rolled it down into the ground, and one guy says, "Man, that's living."
Okay, I'll have to think about that. We'll do a life cycle assessment just how sustainable that is. Okay, so we're back to sea level rise. All right. So Jerry asked a studio class to take on the subject of sea level rise. It was left fairly open, though he encouraged us to try to focus on California. It was to be something that could be brought to the aquarium. It was something that could live here at the aquarium. He didn't tell us what that was, but basically said communicate sea level rise. And beyond that, could could you communicate it in such a way that people might be motivated to push the policymakers and the regulators to adopt certain regulations or push for behavior change. So the students started out by doing, as students do, as design students do, a lot of research as to what's already been done in this area. And it turns out, you know, there are a lot of designers that have tackled this. There's some really neat projects, like here's a paper towel holder where as you pull the paper towels out, the trees, the forests in South America start kind of disappearing. Here's another good one. There's a water cooler, and it's the earth printed on it, and you can see the water disappearing as you drink from the cooler. Some very simple but impactful design projects. MTV did a campaign on global warming, various other campaigns around water and sea levels. Here's another good one, paper towels in the bathroom, but instead of coming out of a plastic dispenser, it looks like it's coming out of the log of a tree.
Yeah.
You know, bleeding that. Are any of you familiar with Annie Leonard and her site, The Story of Stuff? I would really recommend that. I think it's thestoryofstuff.org, and she has an animation in there about sustainability and electronics, and I think you'd enjoy watching that. So they cited this. Oops. And I'm going to go, after all of this research, the students crafted their projects, and I'm going to go right into explaining what those projects look like. And Jerry, if you have comments on each of the projects, just feel free to add in.
If I can think of any more Detroit stories.
No more disposition things, you know. Okay, so this project was called Our Rising Seas. And they decided that their audience, they picked their flock as children. They wanted to explain sea level rise to children, and they wanted to explain it to their parents. They took that group as the audience that comes to the aquarium, so that is who the audience for their project was going to be. How would they go about making children and their parents aware of sea level rise? Well, they wanted to present it in a global and local way, but also make it personal. The message was that it's going to affect both you and the world, that small actions make a big difference, and they also introduced fun and play. And this is something that you'll see in every single one of the presentations, and something I'm going to add to my list of things designers should do when they want to communicate detailed and complex information. Make it fun. It gives you a point of entry. If you can make people laugh about something, they'll take the medicine a little more readily. They had toured the aquarium, and I'm sure all of you are familiar with the NOAA globe that is getting ready to open. And they wanted to, on this outside deck, is where their exhibit for children and their parents would live. They broke it up into a number of components. They would talk about the history of sea level, why it's changing now, so what, things that can be done to mitigate and adapt to sea level rise. And here you can see how they have kind of placed some of their projects. The project on the left has to do with the history of sea level rise. These posters are the why is it happening. There's a hopscotch that also gives you more information about sea level rise. Over on the left is a sea level rise limbo, which I'll explain later what that is. Over on the right is Seymour, that is teaching them about adaptation to flooded areas, and then a milk carton exhibit where you can measure your own, the amount of water that comes out of your shower and how you can reduce the amount of water coming out of your shower. Over on the right, once we get over there, is a set of what I can do. There are these little rubber stamps with icons where children can decide what are the actions they want to take, and they would take that with them. I brought an example of just some of the graphics, again, aimed at children and their parents, just very bright, simple imagery, but with very accurate information to support it. So this was theirs. They're really hoping you go for it, Jerry, just so you know.
So we made the commitment, there were 4 teams,
Yeah.
that we would take at least one project from each team and execute it somewhere within the aquarium. That's the commitment we will honor.
This, I promised to tell you a little bit more about this sea level rise limbo. So on either side, this is to represent buildings, so the infrastructure that's near the coast. This blue bar is the sea level. And when the sea level is high, just like in a limbo game, you could easily, go under the level of the ocean. As you try to lower the sea level, it gets harder and harder and harder to do that. So it was to represent the idea that it will take some hard work to bring those sea levels down. This was the group presenting. We presented here in the watershed classroom. So here you can see one of the students demonstrating the limbo exhibit. Here is one of the students showing the little takeaway where students with rubber stamps can actually decide what actions they want to take. This is the history of sea level, which talks about when we were hunter-gatherers, it was very easy for us to adapt to sea level rise. We just moved away from the shore. And then with an era of stable climates, and as agriculture grew and populations grew, and we built cities along shorelines, that was possible because we had stable climate. And now we're in an era of changing climate once again. However, we have those shorelines already built up with infrastructure. What do we do now? So it was meant, again, to be an exhibit that spoke to both children and their parents and could be enjoyed on that platform outside of the NOAA globe. Their flock was children and their parents. The media was all hands-on. There was no digital anything here. The story that they were telling was trying to convey it's about us. Sea level has to do with us, sea level rise. The information came in multiple layers. On that how wall, they simplified or clarified the global warming data, but if you wanted to know more, you could lift those little clouds that said greenhouse gases, and it would give you more information underneath. So again, layers of data. The activity was, or the action that they were promoting, just do it and have fun. Another group called themselves Carbon Detox. They came at sea level rise from the point of view of mitigating global warming. And these are the questions that they asked themselves. I'll skip through that. And this is the kind of context within which their exhibit lives. You first realize that sea level rise will happen. Then you educate the person to reducing carbon dioxide output or greenhouse gas output, give them mitigation strategies, try to influence them to live a carbon less or carbon-free lifestyle. They envisioned a pop-up exhibit that has two sides. On one side, they would show a map of the world and show where areas of sea level rise are most likely to occur. And they also provided on the same chart this warming curve, the hockey puck, or the hockey stick, excuse me. On the back side of the pop-up were various things that you could do to reduce your carbon emissions. And then they also tried to promote investment in reforestation as a carbon sequestration strategy, and also to purchase carbon offsets. They also designed a table that's supposed to go in the cafe. And so on this table, as you can see, is the map of the United States with a future scenario of where sea level would be. And then they provided, on this table would be iron filings. Do you remember as kids, did you ever play with those, God, what was it?
The man with the head.
The one, no, with the hair.
Yeah.
The guy with the hair, and you gave him a beard and a mustache because you moved that stuff around. Well, it's the same idea here, except it would be, the magnet was below a salt shaker that sits on the table, and you try to move these iron filings to replace land where sea level has risen. There would be data on this table, and here's a picture of children actually playing on the table. And you might recognize some of these folks. These are some of your board members. And here's the table, and they were playing with it to see how well it worked. I want you to notice these napkins here. Another idea they had was they wanted to look at mitigation behaviors. So they came up with green power, consume conscious, and motor less. And then for each of those topics, they would print this on the napkins that are in the cafe. So while you're eating, you could also read something on a napkin. Again, so their audience was the United States. They used both analog and digital because they wanted you to go to, they had a website that supported this project. The story was, it's about you. The information was pretty simplified. The action they were promoting was to pay for carbon, and the fun was have fun while eating. Sustainable aquaculture was the third project. They approached this from a different point of view. In their research, in looking at sea level rise, they discovered some things. One, that as population rises, there's going to be increasing demand for protein. That in California, some of the delta areas that would be inundated would take agricultural land out of commission. That current aquaculture was an unsustainable system, and it also posed certain health risks, the way aquaculture is done today. And they wanted to provide protein for a growing population, but take out, replace cow-based beef protein to reduce greenhouse gases, and to install sustainable aquaculture to replace agriculture that would disappear because of sea level rise. So they were working on kind of multiple fronts here. I'm going to skip through this. So their final kind of proposal was for a sustainable aquaculture system to support support efforts to mitigate global warming, sea level rise, pressures of a rising population. And what they found was this system called integrated multi-trophic aquaculture. And it's being developed in Canada by a man named Dr. Chopin. And it works like this, where in aquaculture as is practiced today, you basically have some fish in a container and you feed them something, and their waste and any of the byproducts of the feed remain in that body of water and collect down at the bottom. In multi-trophic aquaculture, they're trying to replicate natural ecosystems. So not only do they have the fish, but you have mussels and shellfish, you have bottom feeders, you have algae, you have the waste from one system providing nutrients for the other system. So they're trying to replicate as closely as possible a natural system while also producing fish protein. This is not very clear. Let me move that. In addition, they found some economic data that said that this had the potential to bring in revenues of $1 billion a year to the state of California. So they also tried to make the financial case for this. They wanted to brand it. This was the logo of the multi-trophic aquaculture system. This is their proposed logo to promote sustainable aquaculture. And this was the group. The way it would live here, the way they would inform the public about sustainable aquaculture, is they designed an arcade game. And so, see the balls here? You know, where you pull at the bottom? Well, these balls represent nutrients, the nutrients that would go to feed the fish. If the balls go to this side of the gate, that's unsustainable. They go past the fish and just collect at the bottom. On this side, if you go into sustainable aquaculture system, it goes through the various systems and just continues to cycle around. So I have there we go. Lights, they did a beautiful, it's just beautiful. Here is the unsustainable side with the hormones and antibiotics. Did you catch the little three-eyed fish down there? They also designed a little petition, which I'll just hand around, in which you would write your representative to get their support for sustainable aquaculture, and then they also designed a little thing where you cut this apart and you make a little fish that would have been grown in the sustainable aquaculture system. And you could see their logo. So it also was analog. Their story was sustainability. It was simple yet very sophisticated. The action was policy change, because right now that kind of aquaculture, it's difficult to get permits. And the fun was that it was an arcade game. And that brings me to the last project, which I think will just, I'll just make my time limit. So this one was called Think Sink. So they combined the word think. They wanted people to be thoughtful. And they wanted people, they wanted people to also realize that cities were in effect sinking below the level of the oceans with sea level rise. Okay. They wanted to start a campaign about sea level rise. And the first part was to promote this idea of thinking and recognizing that cities were going to be inundated. They were going to raise awareness by means of a wacky exhibition, and we're going to show you some of the wacky things in the exhibition. The exhibition was to get you to go to their website. And at the website, they wanted to start a movement and a whole series of petitions that would raise awareness and adaptation policies related to sea level rise. So why are they doing a wacky exhibition? Well, because here's the scientists, here are the people, there's the scientific information, and that's basically where we are. We don't have a clue because, again, that translation is not taking place. Whereas the designer is able to interpret that information in a way that the public or the non-scientist can understand. And this is one of the things from sea level rise. They designed sea level rise socks. So if you bought the Boston pair, here, the Long Beach pair were a little bit lower. So you would have, each city would have its own kind of set of socks that would be correct in terms of where sea level rise was predicted to be. To make people aware, go to the site, join in the petitions. So this was the sort of structure that they had for their exhibit, with monitors on either side. This was the website. They own the ThinkSync domain name, so we can have a site like this, Jerry, where we can put up information, have little games, get them to
Freestyle above the
yeah. Here is how it would be organized. And these are some of the things they designed. And I brought just a few of them. So there's, you see and we were even thinking some of these things could be sold in the gift store. So here is a coffee container, and this is Long Beach in 2011. But when you put your 2050 holder on it, it shows the water covering Long Beach. So it's a really simple idea, but very impactful. So that's the one there. We also, they designed some sea level rise pens. So depending on how you turn the pen, you see Long Beach being inundated by water. This is one of my favorites. They designed a letter from the future. So this is to Jerry. It says, "Dear Jerry, grandfather, I'm your grandson. We're living on the water. Our sea level has been risen. My mom said to me, because you make a lot of CO2 emissions. Please decrease carbon emissions. Thanks, from your grandson." And here he is, drawn. He's in the water because of what his grandfather Jerry did. This is the letter from the future that you could order up on the site and send us. Pass this around too. Pass this one around. Oh, here I'm going to ask Jerry to volunteer.
Oh, no. I have a feeling I know what this is.
This was another piece for the exhibition. out of falls. You know where that Jerry? Again, to raise awareness about sea level rise. You don't have to keep holding it.
Are you ready to explain how practical it is?
Well, I think it's very practical for when, you know, we're underwater all the time. They designed golf ball seeds, or golf balls where seeds to increase reforestation, Nerf seed bullets. Here are those sea level rise socks, different kind, and they have a nice ridged shape like wave. Here's the coffee sleeve. This is Long Gone Beach. In the future, there will be no Long Beach. So what this is a beautiful crystal vial of sand from Long Gone Beach. Because that's the only beach we'll have left. We'll keep them in little souvenir containers. Here's Celeste. She's the designer of the bikini right here. Here you see Jerry and some of our guests at the final presentation looking at some of the items. Here's a better, she also designed underwear with waves on it. I tell you, the board members could not take their eyes off of some of the imagery. It was really tough. Everybody else was being ignored, but they were watching this. Turns out this guy's an Abercrombie and Fitch now.
They wanted to lower the sea level.
Jerry, I thought you said this was a G-rated group. But so again, with humor, to not beat people over the head with an image of the future that is so horrific, but to get people to begin a dialogue, to kind of bring people together to talk about this subject so that we can begin to implement things that mitigate and adapt to sea level rise. They also designed future flags. So this is the future flag of the United States. Here's of the UK. I like this one, Greenland, because it's bigger. The ice is melting. So they had a whole series of what the future flags will look like. So their flock, they were obviously targeting young hip, which we all are. Their media was analog and the web. The story was that sea level rise is happening. The info was presented in a wacky way. The activity was to join the campaign. And the fun was, well, what's not fun about underwear, right? So just a few last slides on design process. If you've never seen how designers work, this was our classroom at Art Center. These were some of the early prototypes. It starts with sketches like these and goes into prototype. Carbon detox. Again, you know, this is the other instructor, Frida Weissert, giving a critique. We work on the basis of critique. The work gets brought in, and we critique the work, and then the students have another week to come back and make improvements or changes. Here's sustainable aquaculture and all of the various kind of directions they went until they finally settled on the arcade game. And this is Think Sink. This was the original idea for a letter from the future. Here's the pen, but they considered water bottles and then a self-watering system. I mean, for every project you see up here, there were 30 to 40 sketches that supported it and maybe 100 ideas to begin with. But that's how we work. And so to sum up, there is scientific information. It's critical that we understand this scientific information. We need people who are skilled at visualizing that information to translate it for a larger audience, to get it outside of just the scientific realm. That clarity and understanding of the information is critical if we are going to change our behaviors. We have to put it within both a personal and global context, motivate people for behavior change so that mitigation and adaptation can take place. So it is a beautiful marriage of science and design to guide for future thinking, to allow us to guide present action. And I just want to leave this with you. I thought, Jerry, if you're not familiar with this Bob Dylan song, but it's like perfect. I don't know why we didn't, we should have started the class this way. But he was future thinking when he wrote this song. So I leave you with that, and if you have any questions, I'd be happy to answer them. There is this is the group that created all of these wonderful things. Here we are outside after our final presentation.